Okay, hello students. So today we are going to discuss the ballistic conductor. And today we are trying to finish it also. You know that till now we are discussing three type of conductor, no? Like a molecular conductor, ballistic conductor, and micro long conductor. And if you see the molecular conductor, like if you see the molecular conductor, this is also I need a red color. If you see the molecular conductor here, no? So molecular conductor, that actually you understand molecule like hydrogen atom. It consists of a very few number of atoms, very few number, maybe 10 atoms or less than that 10 atoms. In that case, so you assume that you have a 10 atoms and you have a contact on it. Correct. The matter is that if an electron is there and if they want to travel from point 1 to point 2 in molecular conductor, which is very small in length, then what is the main critical parameter is that how quickly they can come into the material or how quickly they can come out to the material from the material. It really doesn't depend how much time they travel or how much time they stay inside this 10 atom strong or 10 angstrom long or 10 or 20 molecular long materials, because it is so tiny it can easily escape through. The main important part is that how much time they travel, what is the critical factor to come inside the material or how quickly they can get out from the material. Like gamma 1 and gamma 2 are very important, and that is actually coming to that molecular conductor. Correct. So here actually you see that we are writing few atoms long, and the transport of electrons really depends. Transport of really depends how quickly it can come out from the contact or come in through the contact, rather than how long electrons stay inside the material. Yes, that's it. Now ballistic conductor is totally different. It may be 100 angstrom or more than that. Most important part is that it should not suffer any scattering. That is the most important part. They should not suffer any scattering. So like in ballistic conductor you have point 1 and point 2. Okay, so the electron should travel from point 1 to point 2 without any scattering, without any destruction, right? In that case both are important. Why? Both means one is how quickly you get in or how quickly you get out from the contact. Yes, that is also critical factor. Another factor is that how much time you stay inside the conductor. Both parameters are very important. Only the difference is that it may not or it should not suffer any scattering, right? And micro long conductor, that is true case, like you see ballistic longer than ballistic conductor, but it is suffering from the scattering. Yeah, so it is suffering from the scattering inside the material, and so traveling time depends on how good the contacts are and how much time it stays inside the material. So difference between the ballistic, like if you look at this is my ballistic and micro and long conductor, is that ballistic doesn't suffer any type of scattering. Ballistic doesn't suffer any kind of scattering, whereas micro or long conductor is suffering from the scattering. That is all. Now in the molecular conductor, how to deal with the molecular conductor, that we know. What is that things? We have deal hydrogen atoms, no? That part, and like we have a series of hydrogen atoms, a series of molecules laying, then solve it for Schrodinger wave equation exactly the same way what we have done. Like suppose we have a 10 atoms long material, you have a 2 contact over there, then you have also gate, so you have a source drain and gate of 10 atom strong 10 atom long material. Then if you apply some gate voltage, so the potential will change. Similarly, based on the change of potential, based on the available of states between that two forming like F1 and F2, the electron will flow from source to drain, like that part. So we have studied it nicely. Ballistic conductor, as you know, there is no scattering phenomenon. It is very, that is the difference between the long conductor and how to deal with ballistic conductor. We have studied previously, correct? One thing that we are actually studying the special case in conductor, that is called the ballistic conductor, that's all. And you know the modern transistor like 15 nanometer technology, they are actually kind of ballistic conductor. Okay. One thing I make sure that suppose you don't know whether it's a ballistic conductor or like a scattering or diffusive conductor, you don't know. Doesn't matter. In that case, you can to solve the Schrodinger wave equation or to get to calculate the current, you can easily, what you can do, you can actually solve it traditional way. Like take the Schrodinger wave equation, then find out the basis and all these things and solve it. There is no harm on it. But if you know that ballistic conductor, like a 15 nanometer, 22 nanometer technology case, you know that it is so small, so it can be a ballistic conductor where there is no scattering effect. And then you can easily or quickly get the solution of the current without really computing computational help. Almost analytically, maybe small thing you can do, but almost analytically you can calculate the current. Okay, that thing actually we are studying. Okay, so and with this study actually, you know, so here actually we are saying that suppose we have a ballistic conductor, suppose we have a ballistic conductor with parabola equidiagram. Now why we are saying always parabola equidiagram, you at least understood like silicon. Silicon is actually called, when if you see the silicon band diagram, it is a kind of parabola, kind of, because you know that you may have this is a very special case for graphene, like it is a linear, very special case for graphene. No, it is a kind of linear, but it is like energy versus Kelvin, K, momentum vector. But almost silicon, if you see, is kind of parabola. Only thing is that you may not have a E and K, means maybe you may have a valence band here because it's a indirect band gap, and you have multiple subband. And what is the philosophy of subband, that you already know. No, that part we have studied. But we don't bother actually like band from other levels or band of, like if it is a complicated band like that. We really bother about what is happening here, because in electrical like you see that in electrical regime we are really bothered this portion and this portion, that is enough, right? Only this portion. So this portion you can guess it like that right, no? This portion only just take small amount. So this is like E versus K. This is very small amount. So this portion you can have a E versus K. It doesn't matter actually. But like here and here also valence band and all these things. So we are really bothered about what is happening here and what is happening here. Correct? So you may have a very complicated band diagram like silicon, but we are really bothered a very small region like here. That's what I'm telling you, it is here or here. We are not bothering what is happening the other part, like this part or this part, because that for electrical characterization it doesn't really require. Yeah, definitely for optical or mechanical purpose you may need. That time you have to go for the full solution, but that's it. And you see this nature is kind of parabola, that's what for general purpose I have taken a parabola condition. Okay. Now, if you have a parabola condition and like you see, and we know 1D solid density of state is proportional to e to the power half, correct? Minus half, because this exercise we have done in last semester. And remember, density of state is proportional to e to the power minus half only for the parabola condition. If it is a linear, like graphene, here is a graphene, no? If it is a graphene or other case, so you understand, no? This is then in that case, density of state may not be linear, may not be proportional to e to the power minus half. That we have just observed a couple of lectures back. So you see that for graphene, we have observed the density of states is somehow proportional to the E. Okay. Especially for parabola case, you see density of states proportional to e to the power 0 or constant. But that is true only for the parabola case. If it is a linear case like a graphene, the density of state is not at all proportional to that density of state for parabola is independent of energy, whereas graphene, it is not independent of energy. That is actually totally a different case. That we have studied, no? Last couple of lectures back we have studied. Similarly, the density of state is proportional to e to the power half for 3D solid only for parabolic lecture, parabolic EK diagram. If it is a, yes, so if it is other type of EK diagram, it may not be proportional to the e to the power. So all these things, if you see, it is true only for if you have a parabola EK diagram. And these things we have studied nicely during our last semester, no? So we have invested a lot of things. Now, if suppose I am considering parabolic EK diagram, then for a ballistic conductor, then what is called the number of modes and how it depends? That you can show. So so computer show that 1D solid. So if you take number of mode for one dimensional e to the power 0 for parabolic EK diagram, for 2D solid e to the power half, and for 3D solid e to the power 1. So you see there will be kind of half difference. So you are actually adding half and half and half. Yeah. So sorry. So you just I have to apply some eraser here. So you see, so it is totally only for parabolic. Only for parabolic diagram. It's not true for others, right? So be careful about these things. If somebody asks you to find out 2D solid, means EK diagram of 2D solid, which is not like the density of state is not like a parabola, then you might end up with a different result. That this dependence of energy to that dependence or number of modes would be totally different. So for parabola, it is actually true, correct? So that you have to measure. Now, here actually one important thing that I would like to start, like if you want to know the current means if you want to know that what is called that conductor, because if you know the conductor, you can calculate the current, because conductor means, like if you apply conductor, if you know the conductor, then if you know the voltage, so you can get to know what is the current, whatever the voltage you have, you can get. Suppose 2D material, so you need to calculate, and that you have to you already had calculated these things in your last semester. Suppose you have a 2D material with parabola, with a parabolic EK diagram, which is common EK diagram of ballistic. It's a ballistic conductor with a 2D material with a parabolic diagram. Okay, and if you calculate the density of state, it looks like this one, right? And these things you have calculated in your last semester, so I don't need to explain how you got it, but that's fine. In this case, so you know the density of states, okay? And this is the case, it's called the equilibrium. So let us see whether I have written, yes, no. So suppose it is in equilibrium because I have not, equilibrium. So this is equilibrium case, and in this case, suppose you have applied, this is actually called, what is the number of carriers, means number of electrons. So it is a JL formula like dE, density of states, multiplied by Fermi direct probability. And if you, sorry, and I think I have to delete it, otherwise it creates some problem. Okay. So so you see, so this is the number of electron that we have calculated. Now, what is actually, now if you do the calculation properly, like if, so you need to find out density of state. What is the density of state? This is my density of states. And if you know what is my Fermi direct possibility, you know that part, no? So that you put, then you will get this number. So this integration you can easily calculate that. So one thing that I would like to mention, that mu factor. This is actually the energy. So what I am trying to tell you that you are calculating number of electrons, okay, in at particular energy, because this is my energy axis, no? So this is my energy axis. So you know, I am calculating in particular energy or particular potential. These are the, I just assume that this is my energy. Okay. So here actually I am telling you, so this is called energy, like I would like to calculate the number of electrons in a particular energy, correct? And since it is in equilibrium, so this energy from here and here both are same, so no issue. So you calculate number of electron and that looks like this. Fine. Now, so this is the number of electron, but what if we need to have, because always we deal with a carrier concentration. Okay. So this is N, and since it's a 2D material, so that we have to consider the number of electrons per unit area. So N by A should have, so that is actually mass 2 pi h bar square mu. That is actually we are called the carrier density, NS. We are quite aware of this part, right? Fine. Now you apply small voltage. So if you apply small voltage, what will happen? So suppose you apply small voltage, little bit of your based on the voltage, whatever the field you have applied, the F1 and F2 distribution will change, or the position will change, and then we need to really find out what is called the current. Because remember, we are after that we need to know what is called the conductivity, correct? So this is our general formula, like for a ballistic conductor, okay, what is the current? So we need to have a mode, and what is the mode? Mode is, you know that mode is actually proportional to the density of state with some prefactor pi h bar Vx by L, right? That we have studied, right? So here you know that mode. So density of states, so that we have already know. Now pi h bar V L. Okay. So that is part. So here if you come back and if you calculate the current at particular energy, and what is the particular energy? That is actually mu. See, you see here I have written mu. So we need to know what is happening at particular, because you have applied very small voltage. Look at that, because we are going to know what is called that conductivity. We have applied small voltage. Once we apply small voltage, there is little bit of change, and we really want to know what is happening very close to my very close to my equilibrium level. Earlier the equilibrium level is here, no? Earlier my equilibrium level here. Now at this very small equilibrium level, what is happening, that I like to know. Now you know that since number of modes, as you know, number of modes is a numbers. Okay, so and if we, so that can be taken out at particular energy. So for an example, how to calculate number of nodes, and that we have done. No? So we have done that exercise nicely, correct? So I'm sorry, there is some issue. Okay, I'm extremely sorry. So how to calculate the number of nodes, that we already did lot of exercise. Let's remember this part. You know, this is so we know how to calculate the number of modes for two-dimensional solid and all these things. We have done a nice exercise on it. So there is no problem for us. So like here so you know that this is the how we have calculated. We know how to calculate this number of steps. Okay. So this is really not an issue here. So we know that part. And another thing is that suppose somebody is telling that I don't know whether I have written or not. Yes. So here, suppose somebody is telling that how many number of nodes are there, okay, at particular energy level. So this is my particular energy level, which is called E1, okay. And so people are asking at E1, or suppose I am writing that sorry, at particular issues here. So you see that at particular level, so you see this is my mu, okay, this level is mu, and I would like to know what is the number of modes. So as I told you, if this mu at particular, this energy is covering how many subbands? 1, 2, 3. This is also subband, this another brown color thing, this is also subband, but this is not covering, so we should not count. This mu is covering 1, 2, 3. This three number of subbands, so the number of mode is 3. So that we have studied, no? So that's not a great deal. Similarly, you know how to calculate the number of modes here. So at particular, and since it is a number, since it is a number, so we can easily take it out of the integration, correct? And this F1 minus F2 is the QV. You know already this part, because this is the amount of voltage you have applied. So this part, okay. So this is actually I is equal to Q. Remember, if this is sometimes people in the expression, whatever the papers I followed, sometimes people have add what is called sometimes people have add called a 2 here, and this 2 sometime Sometime it's not always true. This 2. Sometimes they have added this 2. So this 2, sometimes you see that factor 2, and if you see this factor 2 here, so it is due to the spin. So don't forget, don't confuse. Okay. If you see that factor is coming, so it is due to the 2. Some papers it is written only Q square H ME. Some papers already multiplied by 2. So 2 means 2. 2 spin. Okay. So 2 Q square by H mu by V. Okay. Now in that case, now you have to calculate. So this is your homework. So because you know, I already told you how to write ME. For in this case, yes, you can calculate ME, and ME is equal to you know that ME relation, it is proportional to, so DE into pi H bar Vx by L. So if you can calculate, if you do all this exercise, so you will get ME is like this one. 2 root over 2 ME W, and it is true because if you know the density of states, because you need to calculate density of states, then you have to apply all this factor, you will get this is W by pi. Correct? So this is the factor that you can calculate. Okay, just calculate it. If not, then I'll see. Okay, fine. So this is actually ME. This work will be your homework. Please don't forget it, very important. This would be your homework. Okay. So that is actually, so if once you know the ME, then we need to calculate, that is called the RW. And what is the RW? Remember here you get remember here you are getting I, so you are getting V. I by V is equal to conductor, and what is conductivity, conductor, and what is resistance. So just V by I is the resistance, so you know what is resistance, and you do all this calculation, you will get finally you can show that this is the answer. Just do this part and this would be your homework. So all together you have to solve these things also. This is a nice homework, and I think this you need to do it. Okay, fine. So ultimately you can show it. So this portion, I think I have covered the ballistic part. The most important part is the how to calculate current. You know what is the current and all these things. And you know this, if you calculate RW, R means resistance, and what is the resistance? Can you tell me what is the resistance? Resistance is equal to, can you tell me, rho into L by A. What is rho? Rho means resistivity, and you know the conductivity. So all these things you know, right? You know conductivity from this expression. From there you can calculate resistivity from this expression, and if you know the resistivity, you can calculate the resistance. How? Because you have to multiply the resistivity into L by A, length by area, and you will get, and area is actually function of W. That is why this W is coming. So it is easy to do it, just do it. Okay. So here actually you will get a conductivity. From the conductivity, how to find a resistance? You have to multiply A by L. A is actually function of W. So that is why you get RW ratio. So this is very important. So your conductance is a function of width. It is not at all function of the length. That is ballistic conductor. It is the function of width. How big your this material. How wide is your material, not how long your material. Why? Because just go back and check what I told, or that if you have a ballistic conductor, if you have a perfect, if you have a ballistic conductor and if it is really doesn't suffer any scattering, right? So your electron will transfer from position 1 to position B immediately. So it really doesn't depend like how much time it stays inside the conductor. It reads how wide it is, but not depends how much it how big your conductor. As long as it is actually scattering free, you will get your electron will transfer from position A to position B immediately. Correct? Now before I start, so here actually is important part. So before I start, you see this here I have written ballistic conductor longer than molecular conductor, but it should suffer scattering. Sorry, here actually mistake I have made. So sorry. So molecular conductor, but it should not suffer. Ballistic conductor, it should not suffering. So you see that here it should not suffering any scattering. It should not suffering any scattering. That is very important. It should not suffering any scattering. So that means if it doesn't suffer any scattering, so traveling from position A to position B, it is very fast. Correct? So if it doesn't suffer any scattering, so traveling from position A to position B is very fast. Right? So the formula what we have derived, it is actually this RW, whatever we have whatever we have derived, so RW is proportional to is not so it is not proportional to or not related to length, not so whatever RW we have studied, it's not at all, it is not related to L. But here we have written should not suffer scattering. The traveling time depends on how good the contact and how much time it stays inside the material. So how much time, the moment you write how much time it stays inside the material, that means we have to modify this definition now. We have to tell, so it really doesn't, this how much time it stays inside the contact, please make sure it doesn't depends on the it doesn't depends on the length. So please make sure that it doesn't that ballistic conductor, it doesn't depends on length. No, it doesn't depends on length, rather it depends on W. So that is, so how much time it stays inside the materials, it this, right? It depends only width of the material but not on the length. So this portion you have to be very careful when you write this definition. How much time stays inside the conductor. So normally what we felt that how much time stays inside the conductor means it depends on the length and it depends on the width. But here in ballistic conductor, since there is no scattering effect, so from traveling from position 1 to position 2 is very fast. So it is really independent of L. Okay. So that is actually, so this meaning you have to be very careful here. Okay. Very, very careful. But here, if you say the traveling time depends on how good the contact, means how easily it can come in and come out, like gamma 1 and gamma 2. Similarly, how much time it stays inside the material. That also really, because in this case it suffers from the scattering. Since it is suffering from the scattering, so that means it also depends on length and W. Correct? But in ballistic conduction, it depends only the W. Okay? Right? And here, can you tell me what is happening here? It is really doesn't matter. It doesn't depend on length and it doesn't depend on W. Why? Because it is so small. Okay. So length is actually 10 atoms long. Also, it is so small, it doesn't really matter that electron can easily come from position 1 to position 2 easily because it's very, very small. Okay. So L is kind of independent and W is kind of independent here. Okay. It doesn't depend how much weight is. Okay. So that is the conclusion here. Okay. Fine. So next time I'll come back with what is called the spin dependence and all these things. So I think you please revise your whatever you have studied nicely, and if you have any questions and all these things, so please drop a mail or you can call me. We'll have another interactive session. And important part is to please do the homework. It's very, very important. So just try to do it. Okay. Thank you.